All right, now I'm looking at the second order differential equation intro homework, and I'm thinking that problems 4, 5, and 6, and I'm thinking that I didn't really explain them to you well enough for you to do the homework. And so I want to so I decided to make this video to help you with that. Okay, so that's what we're going to do. Now, the problems 4, 5, and 6, the way they are worded at the beginning, something like, suppose that the following two functions are solutions to a second order linear homogeneous differential equation. Okay, these are the solutions to the second order linear homogeneous differential equation with constant coefficients that we looked at in class today. And that was 2y double prime minus 5y prime plus 3y equals 0. If you want to go ahead and take the first and second derivatives of this right here and plug those into this equation, you should get 0. And you could do the same thing, take the first and second derivatives, in this case of e to the t, which is just e to the t, and plug them in here, and you'll see that you get 0. Okay, and so that's what they mean, is that these are solutions to some differential equation. We know these from class as the solutions to this differential equation, but you're not actually told that. Okay, so now let me explain to you what you're doing. You're computing the Wronskian to see if these solutions are linearly independent. So to see if they form a fundamental set of solutions. Okay, so how do we compute the Wronskian when we just have these two things here? And the question is, what do we put into each of these boxes? All right, so remember from class, we took this differential equation and we wrote it as a system of two different differential equations. And remember, we use the substitution x1 equals y and x2 equals y prime. Using that substitution, x1 equal y and x2 equal y prime, we got the system and then writing that in matrix form, we got that. Now when we solve this system of equations in matrix form, we get a solution vector, right? We get some vector s that solves this. Now that vector s has this form x1, x2. And why does it have that form x1, x2 is because notice here in our system it's all x1s and x2s. Now remember from above here, right, x1 from this substitution, x1 is equal to y and x2 is equal to y prime. So the way that we use the Wronskian, because you think about it, the Wronskian is for systems of equations in matrix form, right? So we need a column vector to check whether we need to use a column vector to use the Wronskian to check if these two solutions, y1, which was e to the 3/2 t, and y2, e to the t, are in fact solutions to the original differential equation. Well, when we do, so we need a way to check if these are solutions to that thing. So what we do is we turn this thing into that, this thing again into that, and we recognize that our solutions look like that. So that's how we turn these into solution vectors. So we take a one-dimensional solution, this thing, a one-dimensional solution, and we turn it into the solution vector. Let's not write that. Let's just write the solution vector as y1, y1 prime. So our solution vector is e to the 3/2 t. The derivative of e to the 3/2 t is 3/2 e to the 3/2 t. And our other solution vector is y2, y2 prime. That's just e to the t, e to the t. Okay, and so what I'm basically saying here is when you go to do this problem, what you do, and there's is you say, okay, y1 equals e to the 3/2 t. y1 prime is 3/2 e to the 3/2 t. y2 is e to the t. y2 prime is e to the t. And that's what you plug in here. So you plug in y1, y1 prime, y2, y2 prime. And what we found for those values were we have e to the 3/2 t, 3/2 e to the 3/2 t, e to the t, and e to the t. And now to get this thing right here, right, you compute this determinant and simplify it down into an expression. I did do an example like that, so you'll know how to do that. And I did basically show you this, but I didn't show you, I think I very subtly mentioned that the solution vector was y prime. And so I wanted to make sure you knew that for the homework. All right, good luck, and remember, office hours tomorrow if you're having trouble.